everyone. Welcome to episode number 687 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by yours truly, Amelia Dalton. Since engineering systems are so completely complicated these days, moving away from old school documents toward full system level models is an absolute must. This week, I'm talking all about the future of model-based systems engineering with Becky Petteys from MathWorks. Becky and I dive into how teams use high-fidelity digital twins to snag problems early, why data science is a huge deal for modern design, and how AI is actually changing model-based systems engineering workflows out in the real world. So, without further ado, please welcome Becky to Fish Fry. Hi, Becky. Thank you so much for joining me.
Sure, I'm glad to be here.
Excellent. Okay, so tell me, what do you think the limitations are of document-based systems engineering, and how are they driving the adoption of system-level models?
Yeah, so I'd say the biggest challenge with document-based systems engineering is how do you look at a document and know how the system will perform? So in the past, right, when engineered systems were much simpler, an experienced system engineer could do exactly that. There was a much more reliance on experience and how it's always been done. But today, systems are too complex. There's too much for one person to absorb and understand and to be able to predict. So system models that simulate address this in a couple of different ways. So one way is that you can see how the simulation will work or how the system will work or not work, as the case may be, if there are unintended behaviors, if the system can get into a bad state. You can also try different things out. So what if we tried to solve the problem in a completely different way? Would it still work? It's really hard to know that without simulatable models to test out new ideas. Another important missing piece in document-based workflows is what happens when something changes. I mean, have you ever heard of Control F change management? Probably, right? You go into a Word doc and you just search for all of the occurrences of the thing that changed. And in engineering workflows, that's pretty dicey, but it's also very common. But with digital models that are linked to each other, to the designs, to the textual requirements, you can quickly see all of the impacts of a particular change to any of those things, and you can be sure that you don't miss anything. And finally, for digital models, they often extend across multiple domains and across multiple engineering tools. So personally, I don't think I need all of my engineering data to live in just one single place. That's often called single source of truth. But I do think that you should know where the data lives, or an authoritative source of truth. And there's a new standard, there's a new version of SysML that was just published last year, SysML 2. With SysML 2, I can actually set up a central repository of my system models and share that across multiple tools, especially some of those tools that will help me with my analysis and verification results. So actually here at MathWorks, we're pretty excited about SysML 2 and see it as a really nice way to potentially ease some of those interoperability barriers that have been making it really hard for systems engineers to get access to some of those models.
So, Becky, how do high fidelity digital twins expose system level issues earlier in the development flow?
Yeah, in so many ways. So, okay, when I'm talking about digital twins in this context, I'm going to talk about digital twins as a representation of a possible system, not necessarily one that has already been manufactured. Digital twin, right? It's a really overloaded term. So I just want to be clear that I'm talking about the possibilities, right, for the system. So with these early twins, a systems engineer can really try things out and play around with a bunch of different solutions and make sure that any given decision will satisfy the stakeholder needs without some unforeseen consequences. I would say that making decisions is probably the hardest thing a systems engineer has to do, and they make hundreds or thousands of them in any given system. There is a lot of risk to getting requirements wrong and building a system that doesn't work or doesn't satisfy the stakeholder needs or doesn't integrate well. So, very traditionally, a systems engineer would go to their subject matter experts to ask questions, to gather information, to help them in this decision making. And that's absolutely the right way to do it. But this process can take weeks, if not months, to talk to everyone and gather all the data you need to make that decision. What we're seeing now is much more extensive use by the systems engineers directly of all kinds of analysis and simulation models. So they might start with a high level notional model of how they think some aspect of the system should behave. And then they can take that to the subject matter expert and start to elaborate it or validate it. Or on the flip side, they can start with an existing domain model that the SME has built out and then generate a reduced order model capturing some part of the dynamics from it so that they can then simulate it in the overall system. And again, right, SysML2, I think, is an enabling technology here, kind of really lowering that barrier between the systems models and those domain models.
So, where do you think model based systems engineering is seeing its fastest adoption, and what are the technical pressures that are driving it?
Mm, yeah, it's really across the board. Everyone is trying to deal with this exploding complexity of their systems and also the need to be more innovative, to try novel solutions, but then also minimize risk. And this is almost impossible with traditional methods. So, Amelia, I have the best job in the world. I get to talk to systems engineers from all different industries, from all kinds of sizes of teams and systems, from tiny startups to huge multinational conglomerates. I really get to see how everyone is dealing with some of these pressures. Let me give you just like one example of this. So the automotive market right now is experiencing a pretty major disturbance. The automakers in China have really pushed the boundaries of how fast and how cheaply they can design and manufacture cars. And car makers across the rest of Asia, Europe, the US are really feeling this pinch. One of the keys in this market is the shifting of automotive software architectures away from dozens or even hundreds of small localized ECUs kind of all over your car, each with some kind of specialized software running on it, to a more centralized or zonal architecture where most of the software is actually sitting on, one big microprocessor or something similar. So this is often called software-defined vehicle. And what it does is it allows for more modular software architecture that can be updated, even over the air much, much more easily. There are so many implications in this shift, but the one I want to talk about is the pressure that this puts on the traditional barrier between systems engineering and software architecture. So usually the systems engineering is done by a completely separate group from the software architecture, using separate tools, completely separate processes. But with this additional flexibility on the software side that SDV kind of enables, bringing these two groups together into the same tool chain enables much more rapid iteration of design ideas, functional implementations, verification. So there's a team at Bosch in China who were able to work off of a single source of truth on both the systems and the software sides and ensure consistency. But also, this is the cool part, they were also simulating and doing virtual testing so they could also ensure correctness even with their very rapidly changing designs.
That makes sense. So, how do you think AI is being used within model based systems engineering workflows today?
There are so many ideas floating around out there, huh? I will try to keep this a little practical though. So I've already mentioned, remember that reduced order modeling that I talked about? That's actually one very concrete area where AI is really useful for creating those reduced order models. And here AI, I'm just talking about, boring old machine learning. And again, this is a really nice way to make some of those higher fidelity models useful at the system level where you need good performance simulation. All right, now let's talk a little bit about maybe generative AI and LLMs. I'll actually echo something that Seth Deland said on your podcast, which is that I think a lot of the automation of the rote tasks is a really good potential area for generative AI. And systems engineers have to spend a lot of time doing these tasks, things like copying and pasting from this email to that spreadsheet, or as we talked earlier, right, about finding and updating, the specifications when a change comes through. These are the kinds of tasks that I think we could actually start seeing Gen AI as well as agentic AI help more with. I will say I've interacted with enough LLMs to know that I don't think they can take the place of a SME just yet. But I could easily imagine being able to use an LLM to search through a library of domain models, right, that have been built and labeled and described by a subject matter expert to see like what's out there that might help me to make a certain design decision. I could also envision, right, analyzing the impact of a requirement or a design change, right? We talked before about the benefits of a digital thread connecting all the requirements and specifications and designs. But imagine you have this great, robust digital ecosystem that Gen AI can then take advantage of to help with tasks like impact analysis. I still think we need engineers in the loop, but I think that letting AI take some of that busy work off of our plates that we don't like to do anyway would be a great benefit.
So, Becky, what role does data science play in managing complexity in modern systems engineering?
It's all data. Visualizing large, complex data sets helps so much with understanding, with decision making, with communication. You need data to create models. Modeling creates more data. Analysis requires data. And the more complex a system is, the more data. Data also mitigates risk if you can use it to assess, to analyze, to optimize. It's all about data.
So, Becky, why do experience based and document driven methods break down for highly complex systems?
Yeah, I mean, the best systems engineer out there just can't anticipate all the ways the different parts of a highly complex system might interact. So there's a professor at MIT, Professor Ali Devek, who gave a really nice presentation that I love. In one of his very first slides, he tells a story about alchemy. So in the Middle Ages, alchemy was a magical art, right? But over time, people started measuring and observing and applying systematic methods to it. And over the course of like 300 years, it gradually morphed into what today we call chemistry. So Ali introduces this story as an analogy to systems engineering and where it is on this journey from alchemy to chemistry, from magical art to hard science, from experience based to evidence based. And he often asks his audience, where do you think we are? And most people answer that we're still pretty early. And one of the things that we have to do to get to a proper science is to start measuring things. And one of the things we have to be able to measure is complexity. So the functional requirements for a fighter jet are much more complex than for the Wright flyer, right? What did the Wright flyer have to do? It had to fly. For a fighter jet, it's got to do a little bit more than that. So functional complexity can then lead to structural complexity of the system, right? And now if we think about Conway's law, which I'll paraphrase a bit here, which is that organizational complexity is kind of reflected, right, in the structural complexity of the system being, designed. So those two things are pretty linked. And organizational complexity can also impact the cost and the time to build the system. So understanding all these like mathematical relationships inherent in these increasingly complex systems is absolutely necessary, but is also not sufficient. We also need to get better at analyzing these complex systems, breaking them down, modeling the pieces, understanding how they interact in both expected and unexpected ways. So this is how systems engineering moves, right, from the realm of magical science like alchemy into hard science like chemistry.
All right, so let's talk about some of those main technical and organizational challenges when adopting model-based systems engineering.
Yeah. Yeah. There's a lot of muscle memory and there's a lot of risk, right? So here's the good news. So MathWorks, right? We've actually been through this before. So I started at MathWorks 20 years ago, which is a really long time. And when I started, we're talking to design teams, right, about using Simulink to model and simulate and automatically generate code for their control systems. And back then, I mean, this was crazy. This was weird, right? You had textual documents that the controls, engineers wrote that the software engineers would define. So it was actually in a lot of ways very similar to systems engineering right now. And we heard all the objections. We can't train people on new tools. That seems really risky. We don't know how to do it that way. That won't work in our situation or application or industry. We heard it all. But if you look at now, 20 years later, it's a commonplace model-based design is. It's in every industry you can think of for the most safety critical applications for huge systems, for small ones and huge teams and small teams. It's actually, I would say today, it's riskier to not change how you're doing systems engineering. It's riskier to also try and figure out how to do it on your own. I would also say it's risky not to look at where the field is going, to aim towards chemistry, not towards alchemy, towards hard analysis, metrics, simulatable models, tight connection to design, right? These robust digital threads. It's also completely doable. Organizations are doing this today and are seeing great results today.
So, Becky, talk to me about the benefits that teams will see when model-based systems engineering is combined with AI and data science.
Yeah, absolutely. So we've seen organizations reduce the amount of time taken in making some of those early design decisions by 90%, right? From weeks and months to literally days and hours. There's this really nice example of this from a team at Eton in India that they worked very closely with our MathWorks India team. But they use simulation and analysis to do those earliest trade studies and to validate the requirements. And they talk about a 15 to 20% reduction in testing time and a 30% reduction in late stage design defects. Now, those late stage design defects are the absolute worst. The worst feeling in the world as an engineer is to build something that doesn't work and then find out it was a requirement issue. The impact to the cost and the schedule and, right, the happiness of your engineers is really tough. And honestly, I am all about keeping engineers happy because that's an immeasurable benefit.
It is absolutely. I 100% agree. All right, Becky, it is time for your off the cuff question. So, if you could have one meal right now, it doesn't matter if it's on the other side of the world, you need a passport to get there, what would you have?
Oh, so okay. Can I tell you about a great meal that I had that I would love to do again?
Yeah.
So my colleagues and I, we were at a conference. It was the Incozy International Workshop. So last year, I think, when it was in Spain. And it had been a long week of talking to a lot of people, and we were honestly a little tired, a little far from home, but the four of us, we went out to this amazing restaurant. It was a vegan restaurant, but it was some combination of like the company and the food. And we ordered one of absolutely everything on the menu, and everything was so delicious. And we had such good conversation. It was such a great kind of capstone to a long week at a conference, but a really enjoyable one. And yeah, it was amazing. And I would love to do that again.
I love that. That is wonderful. Well, Becky, I think that's all I have time for today. Thank you so much for joining me.
Thank you so much for having me, Amelia.
If you'd like even more information about the topics covered in today's show, or to listen to Seth's interview that Becky recommended, I've included a couple links below the player on this week's Fish Fryin' page on eejournal.com and in the description for this week's YouTube episode as well. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EEJournal. If LinkedIn is your thing, I dig it. You can follow us or me on LinkedIn. And we are also on Blue Sky Social and Mastodon as well. And we have that YouTube channel I just mentioned, youtube.com/EEJournal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series, hosted by me. And of course, you can subscribe to our EE Journal YouTube channel as well. Thank you, everyone, for tuning in. If you know of any cool new technology, or heck, you just want to chat, shoot me a line at Amelia, that's AMELIA, at eejournal.com, or post a comment on our forums on EE Journal. For the week of June 19th, 2026, I'm Amelia Dalton, and you've been fried.